Video, we're actually going to try to understand inverse functions and what they are. In the next video, we'll discover how to find inverse functions given a one-to-one function. Let's just go over the definition of an inverse function. An inverse function really is a one-to-one function where its domain is the range of its base function, and its range is the domain of its base function. So what I mean by that is, let's draw a function map here, and here's a separate function map. So they're different, they're separate. And let's just say this is f of x, the function map for f of x, and this is the function map for inverse f of x. And inverse functions are typically displayed like this with a it's not an exponent, because an exponent, a -1 exponent would be the equivalent of this, when that's just not true regarding inverse functions. Instead, this symbolizes inverse. So inverse f of x, and I'm going to give them 5, 6, and 10, 9, 8, and 24. Okay, so with f of x, this is the domain, or x, and this is the range, or y. So you take an input x, and you get an output. You get an input, you get an output, input, output. When you have the inverse of x, this all changes. You still have, well, map-wise, you can keep the numbers on the same side. It doesn't really matter. You can actually change the numbers if you want. But actually, with an inverse function, the domain becomes the range of the old, or the base function, okay? And the range of the inverse function is now the domain of the base or old function. So what does that mean? Well, that means now that this is our input, and we get this. This is our input, and we get this. This is our input, and we get this. Normally we go this way. With inverse functions, we go the opposite direction, the inverse of the regular function. One important thing to note about inverse functions is that the inverse of a function produces the argument. So if we have, for example, f of x, the inverse function, inverse f of x is x. Okay, so if we had, let's change it up. If we have g inverse of g of t, that would produce the argument t, whatever that is. If it's a number, like for example, h inverse of h of 2, it would produce the argument 2. And we could also flip that around. So if we have function j of j inverse of x, that still produces x. It's almost like saying the inverse function cancels out the regular function, or that the regular function cancels out the inverse function and produces the argument, but there really is no cancellation going on here. Finally, I want to look at the graphs of inverse functions in the inverse, and we know we need a one-to-one function, so the simplest one-to-one function I can think of is x cubed, which looks something like that. This is y equals x cubed. Okay, here's x, here's y, and essentially with an inverse function, you're going to flip or reflect the graph of your base function around this line. And this line is y equals x, or 45 degrees, or pi over 4, however you want to visualize it. So I'm going to redraw. So when you flip this, you should get a function like this. Okay. And you can write this. You can write this as, well, if we let this be f of x, then this is f inverse of x. Okay. Now what would happen if we tried flipping a non-one-to-one function? So here's x, here's y. Let's go with x squared, just simple. So we know this isn't 1 to 1, this is y equals x squared f of x. So let's try flipping it along our inverse function flipping line thingy, y equals x. That would give us, this would go here, it would give us this. And this is one reason why we cannot find the inverse function of a non-one-to-one function, because when we do flip this around, y equals x, it produces an unreal function, a function that isn't a function, a relationship that's not a function, I should say, because it fails the vertical line test. It failed the horizontal line test, and because of that, when you flip it, it fails the vertical line test, which makes it not a function, which is really the reason why we cannot find the inverse of non-one-to-one functions.